to spread awareness among school students on the impact of the Indian space mission on the daily life of common man. We are delighted to have with us Professor Shivaji Chakraborty, President of the West Bengal Academy of Science and Technology, Professor Amitabh Gupta, the Honorable Speaker of the Day, and Professor Ranjan Ganguly, member of the West Bengal Academy of Science and Technology. Before we start the program, I would like to request everyone to either switch off their cell phones or set them to silent mode. We appreciate your cooperation. To formally inaugurate our program, we will commence with the ceremonial lighting of the lamp. I would like to invite our principal ma'am and our esteemed guests for the day to join us on stage and light the ceremonial lamp. Thank you, sirs. Thank you, ma'am. I would like to invite our principal ma'am, Mrs. Ratna Biswas, to address the audience.
Good afternoon, dear students. It's an honor and privilege for us, Garden High School IISER Kolkata campus, to invite West Bengal Academy of Science and Technology to keep us in their yearly roster and to make this seminar happen. As many of you know, we were supposed to have it before closing for the summer. We thought we will give you some work which you may do during summer, but somehow man proposes and God disposes. So we were unable to get it organized in April, but I'm very happy that though we ultimately could get it done in the month of July, the schools who promised to be here are more or less here for the day. Before we go further, first let me say sorry and beg apology from each one of you present here for being late by 17 minutes. It was unintentional, but still it happened. Now, today's talk is a science seminar. The reason is to make you believe that science is life. Science is not a subject. Science is art of living. We we inhale, we'll exhale, we open our eyes, we see the nature, we see the universe, we feel the beauty of the universe, and that is science. My dear students, learning is a natural process. We take our birth, we learn how to walk, we learn how to talk, we learn how to call mama and papa without being taught by anybody. But unlearning is a conscious effort. And science play a big role in this process. Science is a filter which enables us to filter superstition from actual truth, from myth to actual truth. And if our brain cells get tuned up to use this filter every moment, every day, every time we are breathing in and breathing out, we don't need any further meditation. Science itself is meditation. So, my young future citizens of the country, my request to you is keep your minds open for this particular afternoon. Keep your thoughts open, keep your questions open, and remember the language we speak is something which we think. So don't hesitate. If you want to ask question in vernacular, go ahead. If you want to ask question in English, go ahead. If you want to ask question, that is something to be joyful about. Because we come to school not to learn how to write answer. We come to school to learn how to ask question. So the day is yours, and of course, to the honorable speaker of the day, Professor Amita Gupta. Thank you so much.
Thank you, ma'am. May I now request Professor Shibaji Chakraborty, President of West Bengal Academy of Science and Technology, to share a few words with our students. Dr. Shibaji Chakraborty did his PhD from Jadavpur University and is a full-time faculty member of its Electrical Engineering Department. Previously, he was the director of National Institute of Technology, Calicut, and has worked at the Technical University Munich. He served as development engineer in Siemens AG in Berlin and also worked in ABB Corporate Research at Ladenburg, Germany. He worked as United States National Science Foundation guest scientist at the Virginia Tech, USA, and as guest scientist at Technical University Hamburg, Harburg, Germany. He is the recipient of the Technical University Munich Ambassador Award, All India Council for Technical Education Technology Day Award, and Jadavpur University Gold Medal in both bachelor's and master degrees. He is presently the Vice President of the Indian National Academy of Engineering and President of the West Bengal Academy of Science and Technology. Previously, he was the Chairman of Institute of Electrical and Electronics Engineers, India Council. He has published more than 270 research papers, authored 3 books, developed 3 online courses, and owns 1 US patent, 4 Indian patents, and 2 software copyrights. Sir, I would request you to address a young audience.
Good afternoon, everybody. Now, before I comment, I would ask a few questions. Don't be afraid. It will not be difficult question. But if you have to give an honest answer, সঠিক উত্তরটা দিতে হবে। কতজন নিজের ইচ্ছায় এসেছো আজকের লেকচারটা শুনতে? এইটা মিথ্যে কথা একদম, হতেই পারে না, তোমরা নিজের ইচ্ছায় এসেছো, টিচাররা বলেছে তাই এসেছো। কজনের ইচ্ছা আছে শুনতে? হ্যাঁ, আরো তো শিখিয়ে দিচ্ছে তোমাদের, তাই তো? এই টিচাররা সব বসে আছে, প্রিন্সিপাল বসে আছে, ভাবছে হাত না তুললেই প্রিন্সিপাল এক্ষুনি খপ করে ধরবে। তোমাদের মতন বয়সে আমি যখন ওখানে বসতাম, আমিও একদিন তো ওখানে বসেছি, তাই তো? তখন এরকম সাদা চুলের কেউ এসে বক্তৃতা দিলে আমরা কি বলতাম জানো? পাশাপাশি বসে, এই দেখো দেখো বুড়োটা এসছে, হ্যাঁ, এসে আমাদের লেকচার দেবে, হ্যাঁ। তো আমরা এরকম আলোচনা করতাম। তো সুতরাং আমি কিন্তু জানি যে ওই তোমাদের মতন বয়সে মানে নিজেরা নিজেরা কি আলোচনা হয়, এটা একটু বড়, বোধহয় ক্লাস 12 হবে নাকি, হ্যাঁ, ভাবছে যে এইবার পাস করে কোথায় যাব, হ্যাঁ, এই সময় নষ্ট করে কি হবে, এই সময় আমি যদি একটু অন্য কিছু করতাম তাহলে লাভ হতো, তাই না? হ্যাঁ, তো যেটা how it is helping. Now this one, you know what is happening? Anybody can say? Recording? No. This is YouTube live going on. YouTube live? So this is YouTube live streaming is going on. It's already live. Everybody can see anywhere from the world. But how they can see? In the world, I am sitting in New York. You can see this. If I can YouTube, or even long. If you know a link, I can just put a link. I can see. How? Any idea? Yes. So again, this is satellite. And satellite is satellite. So it is right now in front of you, but maybe you are getting it. Or if you're not observing, that means you're seeing properly, you're not getting that. So that's what I'm going to talk about. See this, look at this. Professor Gupta here sitting, he is a part of all this. I'm not going to do this. India is performing globally. I'm all talking of India perspective. Look at that. There are three satellite missions. What India is doing, you all of us will have always see. What are the different satellites? You can see commercial satellites, operational satellites, developmental satellites, experimental satellites. There are all these sort of satellites here sending the space for different purposes. We'll talk a little bit out. And you can see at bottom, only we have done more than 100 satellite missions. India has completed 100 satellite missions. Some of them student satellites. An idea what is student satellite? It's not for students. It's made by students. It's made by the students who were sent to space. Then in the middle, you see the launch vehicles, because we have to send the satellite. So you need the launch vehicles. You can't ask USA to send your satellite with all the 100 and all that. So we have different satellite launching. So it is in, right? PSLV, Polar Satellite Launch Vehicles. GSLV, Geosynchronized Satellite Launch Vehicles. ASLV, Augmented Satellite Launch Vehicles. So they are all different categories. They have different purposes. And all is done by India. Somebody who did it in ISRO, one day they were sitting like you in that chair. One day they were like you. Then they developed and reached that stage. Then finally, this is very important, that now we have come to that stage, we are sending satellites of other countries. That means other countries have come to India that you send my satellite to space. And how many?
Might be interesting. I'll try to make it as interesting as possible for you. And secondly, to follow Professor Chakraborty, who is such a nice speaker. So I hope to do justice to all of you. Let's see. And before I start even, I have to thank Professor Chakraborty and the West Bengal Academy of Science and Technology, the IISER Garden High, the Garden High IISER, the other way around, and the students, of course. And I should not forget my old friend, young friend, Riddhiman, who is doing this wonderful job by streaming this event. So here we go. So before I start, I would like you to, the students over here, to let me know how many of you can identify this gentleman. Good. About this gentleman? Oh, you know a lot. And this gentleman? Oh, you can be quiz masters. But do you identify this gentleman? Whose common man is it? Very good. So he is the common man who appeared everywhere, and he symbolizes the poor, downtrodden Indians. Well, not really. Sometimes he's very happy and sometimes he's very, unhappy. But in both the ways, he has been very candid, wonderfully candid. And these are a few cartoons, actually. This is first a critical perspective, the Man on the Moon project. So here it is, the common man, very unhappy. And the scientists are wrecking their head whom to send. And they say that he is our man. He can survive without water, food, light, air, and everything. Okay. So when we started our cyber space program, this was the idea. People thought, why are we wasting money on this when India needs something else? And then after some time, when we landed on the moon for the first time, he says that this is when we launched on the moon. We said that elite space club where we entered that, look, this is in 2014 after the success of the first Chandrayaan mission. He says he's looking, look, he's there with his white cow and he wants to enter the space club. In fact, an American friend of mine was pretty disappointed when he came to bomb Mumbai for the first time. He asked me, hey, I don't find the white cow on the streets, which the Lonely Planet says, but then nonetheless, we are always identified with the snake charmer and the white cow, and here he is with the white cow. And there he is, he has entered with the white cow. He has occupied the South Pole, and we have all the world powers knocking at the door. He said, let us in. Okay? So basically, this is the change in the scenario. And now, this is the scenario, this is the other side. All of us know this young, cute girl, the Amul girl, and she's over there. She's, pretty happy with ISRO's achievements. Okay, so here she is with the DSLV for the lunch, and launch and dinner, the way she does it, and this is after we landed on the moon. So these are some of the other perspectives. So before I go on with that, Professor Chakraborty spoke about the various things about the space program. Now I'm going to give you an idea about the science behind it. Okay, so I'll not make it very boring, don't worry. So now we have to understand certain things to understand how difficult the space science is. The first thing is concept of an orbit. Let's say this is our Mother Earth, the pale blue dot. This is a very high hill on the top of the on the surface of the Earth, somewhere near the pole. I don't know how many of you have read this book, From the Earth to the Moon. Okay, so please do read that book, and that was a science fiction long back, but that is not the way we actually go to moon. So this, if I drop a projectile, I push it with a velocity, it will drop here. Push it with a bigger velocity, it will still drop on the Earth. If I push it with an even bigger velocity, it will come down and then go all the way around the Earth and again start falling down, right? So this is what an orbit is. So as I said, the gun gives the first push by throwing it. Gravity makes the cannonball fall towards the ground on a carved path. Okay? It is the gravity alone that keeps the ball moving towards the ground. Similarly, in the case of a satellite, this is Mother Earth. We take the satellite, launch it with the help of a launch vehicle, and then we give it a tangential velocity so that it keeps falling to the Earth, and thereafter gravity keeps it rotating. Okay? Of course, this is Newtonian concept. I will come to it much later. What else keeps it moving? Now, before we understand this, we must understand that the different kinds of satellites have different orbit types. Okay, and this is blah blah. This is, as you know, this is a low Earth orbit, which is less than 1,000 kilometers. Okay, need not be around the equator and are usually tilted. Okay, we can place it around the equator, but not necessarily so, depending upon which way we want to put it. And obviously, it is used for Earth observation purposes, usually in a constellation. Okay, and similarly, we have polar orbits that are a special case of low Earth orbit. The satellites orbit the Earth from north to south. So this is called a special type of orbit called sun-synchronized orbits. I'll come to a video which will explain everything much better. Similarly, we have the geosynchronous stationary orbit. So they will appear to be stationary because they move at an angular velocity of the Earth. As the Earth moves, the satellite also moves so that it appears to be stationary at a certain space. So if I want to keep an eye on a certain space on the Earth, or for example, I want to keep a watch on what is going on in the Pokhran Desert or something else, or maybe over Pakistan or China, etc., I'll put it there. But if I want a certain, so if I tilt the angle a little bit, you will find that it will still be rotating with the Earth. But from a certain point, it will appear at the same point, at the same time every day. That's true. But it will appear to move north and south because the orbit is tilted, right? As this moves, this also moves. But as you can see over here,
however, most applications in Europe are semi-synchronous flights, which means both period and roughly 12 hours. There are many types of flights with varying size, shape, and function. Moving forward, we're going to talk about two special types of highly defined flights: the LEO sun-synchronous and monoflights. Floating boats take advantage of leverage natural orbital perturbations to make these boats more stable. But before we go into detail on sun-synchronous and mono-orbits, we first must explain the specific orbital perturbation.
this is a food for thought for you. I'll come back with a question.
Recall from gravity education that you reports. So what is the as the satellite passes for the pole, or must have a greater than the total force. This compressor force is low. This torque has two classical orbital paths by distinction of same number, and coordinate. If that J2 dynamics is a function of orbital altitude and inclination, closer the inclination is 10 degrees, less the effect J2 dynamics. Additionally, as the orbital altitude increases, as J2 dynamics, there is one orbit type that leverages J2 effect dynamics. It's unsynchronous flow. The interesting effect happens with inclination between 95 and 105 degrees. In this range, orbit designers choose combinations, altitude and inclination, that cause the grand curve to eastward at exactly the same rate as the Earth rotates around the sun, thus sun-synchronous. The satellites are facing these orbits, they pass over the Earth's equator every day at exactly the same local time throughout the life of the spacecraft. These orbits maintain a consistent shadow effect for ancient sensors looking down at Earth's surface. J2 also affects rotational parity. The shifting parity is a function of orbital altitude, inclination, and eccentricity. Again, just like the graph, the greater the orbital altitude, the less the effect J2 has on
Yeah, so that's about orbits. Now, I leave it to you as a food for thought. I mean, why? How do I close it? It's not working. That's what I did. Okay, so all tab does. Okay, so we are done with the orbits. I leave food for thought for all of you. Maybe when you grow up, you will be able to understand why it happens. Can you guess what is the reason behind the J2 perturbation? This is a fine, healthy satellite moving around the Earth, but we calculate the distance from the center of the Earth, right? So why does the radius of the Earth matter? The radius does not determine the center of the Earth, or does it? Just give it a thought and let us know if you can unravel this. Okay, so this is ISRO Star Trek. I called it the Star Trek because we began in the 1970s, and in 50 years we have not only reinvented the wheel, but we have, make the wheel run much faster for us, and this is something phenomenal. Okay, so in 1970s, when I was a kid, we had Aryabhatta, Bhaskara, and Rohini. You have heard the name of Aryabhatta, perhaps all of you. And then we had the Rohingyas, but the real revolution started with the INSAT. So I was a kid then in the 1980s, and I believe we had a large number of cartoons coming on TV, and they were telecast on for our national program. As early as 1986, we had the He-Man and Masters of the Universe, and it is said that around that time we had a number of mega serials also. A little later in the 90s, we had the Ramayana and the Mahabharata. And before that, we had one serial called Bunyad. And the story goes this way, that when Bunyad was played, streets in Pakistan were almost vacant because everybody were glued into the TV screens. So this is what I wanted to show in this. As you can see, once again, the common man. I'm really worried about this TV habit. Actually, it's gone for repairs. So this guy is so much addicted to TV that he doesn't notice that the TV has gone for repairs. And this TV addiction is a cause of the INSAT revolution. As I said, the national. Then I was, I think, in ninth standard, little younger than many of you. And then we had the TV coming in INSAT satellite, and then we had a whole lot of programs coming in. I mean, I think many of us are contemporary. Some of your teachers are contemporary with me, and you might be remembering Hamlo, Bunyad, Karamchand, then Chitrahar, and so on and so forth. And initially we started with terrestrial transmission, but then we switched on to satellite. And then with 9 geo satellites, the INSAT is the constellation is the largest domestic communication satellite system in the Asia Pacific region. Okay, and if you're talking about money, this is the net worth of the productive services in the media and entertainment sector. It is about 3.85 trillion in 2024. I think it's 3.85 trillion is 385,000 crores. I think it's way more per year, and that's way more. I think orders of magnitude on more than what we spend on ISRO. Okay, so that's a little business sense. I have not counted the amount of money that we save by sending our satellites with our own launching vehicles, and also the amount that we earn by selling the satellite services to others. So finally, we have something to be, I think Professor Chakraborty talked about the GPS. There are 24 such satellites. And we are this is BIDO. This is one I have spelled it wrongly. So it's BIDOU. This is the Chinese star which guides the sailors. Okay. So this satellite is perhaps the largest now with 31 satellites. It's one of the largest constellations. Galileo is the European Union's, and this is GLONASS, the Russian. This is, of course, GPS, and we have our own IRNSS. Now, the need for an Indian regional navigation satellite system arose during the Kargil War in 1999, when we wanted some help from the Americans. We wanted them to tell us where the Pakistani bunkers are located, and they said no. And they even jammed the other GPS signals. Then we tried the Russians. The Russians said no. Then finally we got some other. We had the MiG-25s, which were equipped with fantastic imaging capabilities. We did recce from a high altitude, and then we got through. But then the need for regional navigation system was filled, and we had the IRNSS. So the IRNSS actually is our local version of GPS, and as Professor Chakraborty said, that even the GPS uses IRNSS or the NAVIC. And here I have the old man asking very humbly a very simple question, but a very difficult question. Sir, could you please let me know where I am and what is the correct time right now? So let's see how we do it with the help of modern science. So first, let's see how we do it with in 2D. So this is a spherical coordinate system. For those of you who are familiar in the higher classes, so this is our art, right? So I have one angle which tells me which is the latitude, which is the longitude, right? So as I move the longitude, you know, so many degrees east, so many degrees west. That's this angle. And then as I go up, you know, I have another angle, the phi, the theta, which tells me what is my longitude, right? So I need to know the latitude, longitude, and then I may not be on the surface of the earth. I may be on the top of a hill, okay? And then how do I find out my position? I may be, as Professor Chakraborty says, I may be languishing in Darjeeling and claiming to be in Kolkata, right? So I need to find X, Y, and Z, all of them, okay? So if I want to do that, here's what I need to do. Finding position in 2D. Okay, so I need 4 satellites actually to tell me the complete decision. These are the constellation of satellites moving around. And then so my position, this is my phone with a receiver, you know, and I need 4 satellites to tell me. So why do I need 4 satellites? Let's see. So this is the first question, where am I? So this is one satellite hovering by, and it sends radar waves, okay? So let's see how it sends the radar waves. At t equal to 0, the radar wave starts, and the radar waves come and reach me at some time, okay? So this is where the radar waves come and reach me, okay? So at t equal to 5, I know the radar waves have reached me. And if I know the satellite's position, so distance is speed into time, I know how far the satellite is. Similarly for the other satellite, so I know this is in a circle as I just drew it over here. Similarly from the other satellite also, I know what distance am I in. And if I draw this, then obviously I must be on at a cross section of this or this. Now, if I use the third circle, okay, which is the Earth's curvature, then I know that this is an extraneous point. Okay, so this is how I know. This is Alt tab. Fine. So now what we need all the 3 coordinates, and if I do need that, then I have to do something else, and that's finding position in a 3D. Okay, so that's called trilateration in 3D. And over here, actually, I'm on a different surface, much bigger surface. So I find the first this is actually a sphere. Instead of a circle, I use a sphere. I use another sphere. So the intersection of 2 spheres is a circle, which I found out. So I'm here somewhere on the circular plane. Okay, my altitude is still not known. So I get the third satellite to tell me where I am, and then I use the Earth's curvature, which is the 4th one, to tell me where I am exactly how far I am from the Earth. So if I am languishing in Darjeeling, I'm caught, because the altitude itself will be more, and people will know that I'm here. Okay, so I know all the X, Y, Z, and everything over there. Now, the point is that the whole thing depends upon the time. The time, measuring time is a very important job, right? So speed is the velocity into time is the speed, is the distance. So if I calculate the distance wrongly, I will be offset. And mind you, light travels at 300,000 kilometers per hour. And even if I'm off by a second, 300,000 kilometers per second, And if I am off by a second, I would be somewhere in the space, close to the moon. So that's really not very desirable. So we have something called time offset correction. So what is time offset correction? Let's see. So we have an inaccurate clock over here, and this clock is very accurate. This is usually an atomic clock. And I'm going to show you a video to show how exactly an atomic clock works. And this is an inaccurate clock. And the offset is, let's say, A. So distance is speed into 5 plus A. I have taken 5 seconds, but there is an offset because this clock is inaccurate. If you tell me that you want to have an atomic clock on your mobile phone, well, that's quite impossible. So this is this. And therefore, what I do is with the fourth satellite, I have four sets of equations, and I can find out, eliminate this A. So 3 sets of equations for X, Y, Z, and the fourth one for the A. Okay? So this is how it operates. Okay. So now the common man and space-time. As I said that we use an atomic clock. Okay. So if you have seen a computer motherboard, or if you have seen that your watch, it uses a crystal. This crystal usually receives a jolt, and then it generates a specific number of pulses per second, and which is processed by an oscillator circuit. But then this is not, it usually drifts by a millisecond in 45 days, causing a location error as large. If I'm sitting here, I can easily lie to Professor Chakraborty that look, I'm someplace 300 kilometers away from of my choice. So that's really not the one that doesn't work for us, and therefore we use an atomic clock.
Tell the time properly. The clock relies on the tell the time properly. The clock relies on the oscillator moving back and forth at the same frequency over a long period of time. In this case, the oscillator is the pendulum. So I'm going to try to get 2 clocks going to see if they can keep time together or if they're going to have an error. You might see they start off together, but very quickly, we're starting to have some errors build up. A pendulum clock may work for a short time, but it accumulates error very fast. So we need a better oscillator than a pendulum.
Enter quartz. In a quartz watch, the oscillator is a tiny tuning fork made of quartz. When jolted by electricity, quartz oscillates or ticks at precisely 32,768 pulses per second.
A quartz oscillator is better than a pendulum, but it still accumulates error. That could be due to vibrations and temperature changes. So we're looking for a clock that can stay accurate for a long time under unpredictable conditions and can't be reached by humans to be reset if it goes wrong. And that's what we need for a clock in space.
In addition to a quartz oscillator, every atomic clock contains key components that make it work.
What we've laid out are the components of what's called the physics package.
A broadcaster, like an antenna or a horn, shaped like this. An atomic vapor cell, in this case cesium. A light source, like this laser diode. And an electronics package. When exposed to microwaves, cesium atoms oscillate at over 9 billion times per second. And since the cesium atom isn't subject to weather or manufacturing deficiencies, it helps the atomic clock keep the perfect time all the time. Here's how. As the quartz oscillates, it sends out an electrical signal that's used to create microwaves at an exact frequency. The microwaves are then broadcast onto the cesium atoms in the cell. The microwaves will have a certain frequency based on the ticking oscillation rate of the quartz. Depending on the frequency of the microwaves, the cesium atoms will absorb more or less of them. The laser then measures the state of the cesium atoms and communicates that info to the electronics. And an electric pulse is then sent to the quartz to get it going at the right pace again. This correction happens once per second, keeping the atomic clock on time for years.
This is a replica of the actual atomic clock that is currently on our GPS satellites.
So that's what an atomic clock is used. But we have a problem. Now the problem is caused by the time dilation. Now I forgot to mention, I forgot to mention another gentleman who has made everything possible, and that's Albert Einstein. That gentleman sitting quietly with a big beard and with his pipe, he visualized some things that we couldn't think of. And how he did, we really don't know. And it's very difficult for me as a common man to understand what went on in his head. So I'm trying to explain you as best as I can. So imagine that you have, this is yourself sitting on the ground, and you have a ball with on a train which is running with respect to 10 meters per second. This hat with X means it is in the X direction. Okay, so this is in the X direction. So I have been mathematically perfect in putting the X over here, and so now this ball with respect to the again in the X direction. So the observer on the ground sees the ball moving at 15x meter per second. However, if this observer, if this person over here uses a flashlight, okay, then the photons are seen to be moving at a velocity c, which is the velocity of light and not any faster. This is called invariance of the velocity of light and the cause of all of our problems. The problem when you grow up, you will probably learn Lorentz transformation. So the clock on Earth, satellite moving at 14,000 kilometers per hour, actually, but what we have is by each time the photon strikes the detector, we get a tick on the clock. Okay. So what is happening is this is moving at the speed of c, which is the velocity of light. Okay. Now this started from the Earth-based perspective. This started at this point, but after some time, which is very high, very small, it has moved. The velocity here is pretty low, but the velocity here is around 14,000 kilometers per hour. So what happens is this point where it strikes the mirror has moved a little more. So this light has to travel a little more. So if it strikes a little more and then we have a tick, so the second slows down. And this causes a clock in space run slower by 7 microseconds per day. Okay, there is a mistake over here. It's 7 microseconds per day from the Earth-based perspective. And as I've said, even though the photons travel at the same speed, invariance of the speed from the perspective of the observer on the Earth, it has to travel a longer distance. The clock on the Earth-based observatory, on the other hand, records the correct time. So every second is a bit longer. So the clock will read slower. Okay. Similarly, for an observer over here, the Earth moving at a high velocity will, if we could see this clock, this would appear to be slower. But we are bothered about the detection on our GPS systems. So we'll bother about this shift of 7 microseconds from the Earth-based perspective every day. Now there is something else. All is not over. As I said, this gentleman amount of research employment, by publishing first his special theory of relativity, where he took the relative motion between the two bodies into account for explaining time dilation. And later on, he published the general theory of relativity, which takes into account gravity as well. So this is our Earth, this nice little sphere, the pale blue dot is Earth. And this is the space-time fabric. Now, why do you call the space-time fabric? How do you do this? Now, these are all the permissible. So if I take a point, and then if I say that in every instance of time t1, I can be, let's say, in any point within this cell. Next instant, in the next point, again a series of points within the cell. So this entire fabric designs actually tells me the total number of places I can be at any instant of time when the space-time curvature is due to the space-time curvature. And what Einstein said further is that gravity is nothing but the manifestation of the space-time curvature. What he said is that a massive body will bend the space around time curvature around it, and the satellite, even a push whichever direction it is pushed. But because the space-time is curved, it has to move around the Earth. Okay, nothing like nothing else. So similarly, you know, if the Earth moves around the Sun because of the same reason, because it is destined to move in that space-time curvature. And he further says that if you try to apply geometry over here, you will find that the time has to tick faster over here when the gravity is lower. Okay, if further with time has to tick faster. This I will spare you the ordeal, because you will have to figure out how it does when you grow up. Okay, let's wait for that. Again, 45 microseconds per day from an Earth base. So again, from an Earth-based perspective, this will move. So what will we do? Space clocks are adjusted to run at 38 microseconds slower on Earth. We adjust the space clock on Earth so that its ticks are such that it is slower by 38 seconds per day. Okay? So then we get the correct time. Now, as I said, the common man's benefit. What are those? I think Professor Chakraborty has already told us about it. But the part which is very important is that IRNSS synchronizes time for our power grid. Okay, so the power grid which gives us, we have a power grid running across the nation, and the time synchronization is very important because the sequence of events need to be analyzed once there is an incident, and for that time synchronization is very important, and this is what the IRNSS does apart from other things. Now I just put something for your comparison. This is our geoportal, which is Bhuvan. Now can you identify, this is the Victoria Memorial area, right? This is the Victoria Memorial area. These are the ponds that you see over here. Here you have somewhere the St. Paul's Cathedral over here. And this is the race course. And you have some clouds, which of course could not appear over here because this is Google Earth and this is our Bhuvan. So do you think they're comparable? They're comparable, right? So you can use Bhuvan also for all the purposes that we need. In fact, as Professor Chakraborty said, I was not knowing that GPS uses Navic in India. So that is why probably this is much similar. But this is with 100-meter resolution. This also is with 100-meter resolution. You can go down to 30 meters very easily, and you can actually identify all the landmarks over here. Okay, in the same way you do. Now, seeing through the clouds, it's not always easy to see through the clouds. So on a clear day, you have a clear picture, you can get all this. The cartosats will give you everything. But if you are not on a clear day and you want to see through the clouds or during the night, then of course it's not possible. So for example, we want to, and this of course has a military use also. If I want to find out, who's actually aiming a missile at me, a missile is much bigger than 2.5 meters. So I can find that out at any time of the day up there from the sky. Okay. So this is done by this is again done by RESATs. And I would request you to take a look at this. So this is the electromagnetic spectrum. This is actually a gamma ray or an X-ray with the wavelengths over here. The frequency also will increase in this direction. This is radio waves, which is 10 to the power of 3, which is a beta, which is very large. Okay, radio waves. This is microwave radio. We use it for TV and FM over here. This is microwave, which is used for most of our digital communication. And we have the near infrared also, and for radar imaging. The reason why it is used is that if you calculate the absorption of the wave in the atmosphere, you will find the attenuation or the absorption is pretty low in the infrared and this microwave region. So we choose this microwave region for absorption for our purpose. In so doing, what we do is this, that we have a radar disk. This is a satellite called a RESAT. So this radar disk, this antenna actually beams microwave to the Earth and gets back. So as you can see, if the wavelength is large, it will require a large antenna. And therefore, this antenna has to be very big to port on a spaceship, which makes it impractical. But what we can do is very clear. I just kept a picture over here. This is the inundation in Lakhimpur district in Assam, 2012, around the Subansiri River, and this is taken by RESAT 1. These are all watery areas, okay? And as you can see, this is where the flood water is accumulated. And we can actually see this from the surface, okay? So let's see this for the SAR and benefits for the common man.
June 2022, northeastern India, Bangladesh. June 2022, northeastern India, Bangladesh experienced one of the harshest floods of the past century. Monsoon season led to torrential flooding and streets and houses were underwater, leading to more than 2 million people. It also means we can't see the full picture of the situation. Monsoon weather like this leads to shutting down airports, making it harder for planes and helicopters to fly. Traditional satellite images are also pretty much obscured by the massive clouds pouring water. That is until we look at radar and satellite images. These radar images allow us to see the full extent of events and floods as they're happening. You may know that radar is actually an acronym. It stands for Radio Protection and Ranging. Radar is what's called an active sensor. It's emitted, in our situation, it's microwave light. It bounces off objects, and some of it makes its way back to the antenna. We can measure the time it took for the pulse to travel to the object and back, and convert that to the distance. We know that the wave travels at the speed of light, which is a constant speed of the known one. So the longer a response takes, the further away an object is. This is where the first concept of resolution imaging comes in. As I said, we can measure the distance at which objects are, but there's actually a limit to how close two objects can be together before they look at the same echo to our antenna. That's what's called the range resolution. Radar emits a wave in all directions, and we can measure the distance from objects, but we have no idea what direction. This is where the first bit will really cover engineering. In a similar fashion to a camera lens, we can actually focus the pulse to only be emitted in a single narrow direction. Now, any response we get from the antenna means that an object was present, but only within that narrow viewpoint, nowhere else. By the way, spin that around, and you've got yourself radar that can give you an object's direction and distance. And probably also looks. Okay, this is great. We still don't have anywhere close to our Bangladesh image. To create an image, instead of having a single antenna rotating around on a fixed point, we can line up multiple narrow viewpoint antennas next to each other. Each antenna on its own has that narrow field of view, but put together they can cover much larger.
This is what we do with a satellite. As a satellite moves, it calculates the images.
All the way back in 1980, the Soviet Union launched Cosmos 100, a satellite capable of producing radar images with a resolution of a whopping 2 kilometers by 1.5. That meant that this smallest features and objects we could individually tell apart in those images have to be 2 kilometers by 1.5 wide. Such a satellite is somewhat useful, but compared to some of the best optical satellites, even back then, to see less than a meter, it's like comparing the accuracy of a stopwatch to that of a sundial. It's useful, but only up to a certain very limited point. The resolution of these early radar imaging satellites was limited by a number of factors. I think we've made that quite obvious. For now, let's focus on what we've already touched on earlier. How narrow was the used? Well, actually, interestingly enough, the physics that define this angular resolution is the same as for optical cameras. To explain this a little bit more, let's go back to Darren and to our story.
The equation that defines the angular width of any radiated element is lambda divided by d. So lambda is the wavelength, and d is the diameter of the mirror or the diameter of the antenna.
By the way, the visual lights
Here's the problem.
have
Here's the
Armstrongs.
problem. The problem
Okay,
is
moving to
that
microwaves,
origin,
they're much
lambda
bigger.
divided by d, our wavelength will now change from nanometers to centimeters. A massive scale. If we want to retain the same resolution that we have with our camera, our optical camera, we have to make sure the antenna or the mirror also scales up by the same amount. And that's the problem. The problem then is, how do you take this antenna or mirror for your optical imaging system, looking over Russia? It's now got to be many, many kilometers long. How could you possibly do that?
At first, they didn't. That's why these first radar imaging satellites from the 80s we talked about earlier had such low resolution. The wavelength, lambda, in our equation, now became a lot bigger. But since there's a limit to how large we can physically build an antenna, the resolution can never be as that. And it's not just about building a large antenna. At some point, the physics needs to be engineering and the logistics. Our antenna needs to physically fit on the top of a rocket, survive all the vibrations of launch, and work on its own in space. Long story short, we need a different approach. You two clever bit of engineering too. The solution gave its name to how we call these satellites and these images. SAR. It stands for Synthetic Aperture Radar. And by the way, yes, this is an acronym of an acronym. Don't judge the engineers by how the name's done. Instead of building a giant 100-kilometer antenna, people figured out that you could take a smaller one and record the data they emitted and received along the distance equivalent to this original giant 100-kilometer antenna, making it a virtual or synthetic antenna in a way. We then only process all these pulses into an image once the satellite covered that whole area of our original large antenna. Our satellites are orbiting the Earth going at about 7 kilometers per second. And that's per second, not per hour. So now, all of a sudden, 100 kilometers is, quote, just about 15 seconds, recording all these signals and processing them all at once, as if it came from a single signal. That's why it's called synthetic aperture. Aperture, like in photography, is the size of our lens, in our case, antenna. We just build it synthetically by combining many small antenna sizes. You can think of this a little bit like how night photographers take long exposure images to.
Okay, so that's about the. I'll just cut short because we are running short of time. Just a minute. I think I need a slideshow help. Where did you go? अरे shift F5 काज करते हैं. Slideshow. Thank you. Okay, thank you, Ranjan. So now I will just wind it up with the last bit where I was fortunate to be associated with, and that is from the Earth to the Moon. And as you see that, so how many of you can recognize this fellow? Well, I'm very thankful to you that it didn't tell me that it looks like you. Well, nonetheless, so as you can see that this is what happens, this is Earth, and we actually fire the rocket slowly, slowly increasing its eccentricity. And then we fire a slingshot over here. This is called the translunar orbit. And then by the time we have to calculate it, so by the time it reaches here, this pretty lady drives by and grabs this fellow, and then it is in its wave, and then it slowly descends, okay? So the events causing trajectory maneuvers are triggered by communications with Mother Earth with varying latency, and they're fine. So this is what it means. And then once it is here, this is exactly what happens. It was moving towards the moon, it has to turn turtle and face the moon. This is what Captain Haddock is being schooled about. Professor Calculus is explaining so seriously to him. So what we have to do is this, that we are actually starting